talked to Professor Mohan. He told me I can use this slide. It's from his book, and I'll ask Arnold to upload this thing on the course website. We're not going to use all these slides, but some of them are very useful, and we're going to go through those slides for the single phase and three phase inverter. One person asked me about which book should I buy. I have put like I don't know how many books, 4 or 5 books, for this course. What book you should buy is, this course is going to be a little bit from here, a little bit from somewhere else, and it's kind of mixed. It's very difficult to just have one book as a reference, But the one I recommend you, if you're going to buy, is the Ned Mohan book. That book is a very good book. The other one is by PC Cross, Analysis of Electric Machinery. That one is also a very good book. These two, if you're going to have, already we have a Daniel Hart, and the second one I recommend is the Ned Mohan book, and the third one is the Analysis of Electric Machinery by PC Cross, Paul C. Cross, and he was a professor at Purdue University. He's retired. He's emeritus now. And Scott Sudorf and Wozinchek and Picard. They are the authors of that. They have a new edition. That's a very good book for those people that are interested to work in the field of motor drive, electric machine, and those kind of things. It's a very, very good book.
So I realized you can actually read the whole board. I'll just turn the camera.
Oh, okay. That's good. I'm going to use this table for going through some examples. Your Daniel Hart books also have this table, but not as complete as this one. This is a very, very complete, table. Let's start. Let me see where did I finish last time. I was going to give you homework, but I thought I'll delay it a little bit because I want to cover all the PWM things also in the homework. Would be one homework, but let me see. Yeah, we talked about the sign PWM. We defined the MA and MF, what's the MA, MF, and how the output voltage is going to look like. Now let's go through, and they call it bipolar. I forgot to explain why they call it bipolar. If you look at the VO, either is a VDC over 2 or minus VDC over 2. They call it bipolar. There's a plus minus something. You know what I'm saying? That's the reason they call it bipolar. There is another one, we'll go over that, is the unipolar. We'll explain that one, by end of today. Now, let's see what's the relation between the input and output voltage. What we explained, we said, okay, we have, for example, in the half bridge, we had this one. We said, okay, let's call this one O, let's call this one A, and let's call this point M. And this is the VDC over 2, VDC over 2, S1, S2. We said how the sign PWM works. We have a carrier waveform. We call it V control. We have a carrier waveform. We have a control waveform. We call it V con. And we have a carrier waveform. We call it VTRI, or triangular waveform. It's going to be like this. and we define the MA, MF, all those kind of things, right? We said the VAO, if this is a V control, this one is a V con, and this one is a VTRI. We said if V con is more than VTRI, S1 is on, and if V con is less than VTRI, S1 is off, and we know S2 is S1 not. Right? This is what we have. I'm not going to plot the waveform. Basically, if this one is on, this VAO is VDC over 2. If this one is on, sorry, if this one is off, this one is on. So how much is this voltage? Minus VDC over 2, right? That's what we have. If you're going to write it here. So basically, in this case, VAO is a VDC over 2, and this case, VAO is minus VDC over 2. But I want to make it a little bit more general. This is for a half bridge. I'm going to explain this one. For this one, later on we can use it for a full bridge, we can use it for 3-phase, whatever. Let's go with a VAN. How much is a VAN for this case? How much is a VAN if this switch is closed? If this switch is closed, right? This point is connected to plus, right? And this point is connected to, sorry, N, then we're talking about VAN, right? And this one is connected here, right? So how much is the VAN? VDC. And in this case, how much is the VAN? 0. If this switch is connected, right? A and N, they are shorted together, right? So VAN is 0. Now, let's write the equation. I want to see, we explained the MA, MF, all those kind of things. The one is very important for us, always, is the fundamental harmonics, right? The one is going to be related to this one, Yes, we are going to have a output harmonics. We are going to have some voltage, some of the things. But the one is very important for us is the fundamental, right? Now, let's see how we can find out how much is that. Unfortunately, I cannot show you in my laptop. I made a simulation case to show you. When this one is very high, at the end, if that class is available, we can go over to show you over there. If this one is very high, you guys, you come zoom in here. Basically, this sine waveform is going to be like a straight line. I don't know. I can pass my laptop here. Because it's crazy. Because it's a little bit difficult for you guys now to understand now, but if you see that simulation, it will be very, very easy to understand. When I pass you this simulation file, because you need to do the same thing almost in your project. You cannot see it, I'm sure you cannot. I'm going to pass it here. You can see in the piece inverter, there is a 3-phase inverter, doesn't matter, it's a 3-phase or single phase, that one really doesn't matter. This part, the bottom part, is the control part. There is a 3 sine waveform here. I use it for the 3-phase system. And there is a triangular waveform here at these two here. I'm gonna run this simulation now. I'm gonna run this simulation, and I was supposed to show this on all of the board here. No, I didn't know we were gonna have an HDMI cable. And what I'm gonna do here, I'm gonna plot the V control and VTRI, those two. And V control. Let's plot them separately first. V con and VTRI. Here I selected this is 60 hertz and my switching frequency is 6 kilohertz. 100 times of my fundamental. And I'm going to plot them on top of each other. Econ and VTR. See here, I am sure you know lots of you cannot see. There is a sine waveform from top on top over there. There is a VTRI which is a triangular waveform, and here just I plot them on top of each other. What I'm going to do here, just I'm going to zoom in on one part of this one, and I pass that one to you guys. You can look at it. See, I went and select a small part. You pass this one now. Look at this one. You can see the blue one. Let me see the bottom waveform. The blue one is the VTRI, and the red one is the V control. You can pass it in one. If you go zoom in here, you can see over there. The blue one is the VTRI, and the red one is the V control. Yes.
So do you change the amplitude of V control?
That one is full control later. You know, right now we are working with a sine waveform has a fixed maximum, right? But to control the inverter later on, we have to change this maximum. How much is this maximum? Now, in that case, you are going to see if you zoom in, you are going to see something like this. Basically, V control, you are going to see it almost constant. That's the, I think, red color over there on the bottom graph. You can see this is almost constant. And now you see your triangular waveform is like this. Let me exaggerate it here. It's going to be like this. This is a V control, and this is the VTRI. On the computer, you can see this is the blue color, and this is the red color. Now, I want to calculate the relation between the first harmonic, VDC, MA, MF, all those kind of things. I want to see what's the relation between this parameter. So this is a one cycle. No, not this one. Yeah. This is a one cycle of the VTRI, right? The frequency of the VTRI is the switching frequency. If this is a 10 kilohertz, we turn on and off with a speed of 10 kilohertz. So let's call this one TS, which is 1 over Fs. Fs is the frequency of the triangular waveform. In that case, you will see over there is 6 kilohertz, what I have over there. Now, this is TS, this is the Fs, and we know during this time, what is going to happen? The control is more than the carrier waveform, right? So basically, S1 is on, right? If S1 is on, let me do that. Before it is not clear. Let me put it here because I need to put more. We have a V control, and I have. I'm going to do this way. I'm going to go like this. This is the control, and this is the PR, right? Let's come here, VAN. So during this time, how much is the VAN? During this time. Why? Why? Because V control is more than VTRI, right? So if V control is more than VTRI, right? The switch S1 is on. If switch S1 is on, means VAN is VDC, right? So VDC. And during this time, how much is the VAN? 0. Why? Because VTRI is more than V control. Again, here is on, right? And it continues because this one is going to go like this, right? And again, here during this time is off, and here again is on, right? Now, let me see how they plot this one. I'm going to calculate this. Let me calculate. So basically, this is a T on, right? This is a T on. I mean the time the switch number 1 is on, right? And this one is a 1 cycle. This is the TS. Is this correct? 1 over Fs. This thing you cannot find in any book, in any book like this. There is no, I have not been able to find any book to explain it like this. You know, this is just I did it myself. You know, this way. Now, how much is a VAN average? Somebody tell me. How much is VAN? Is it T on over TS VDC? The average, right? Like a DC to DC converter, like buck converter, how much is on, how much is off, how much is the cycle times the VDC, right? So this one we call it DA, duty cycle for leg A. This is or point A. Because later on we're gonna have in the full H bridge we're gonna have leg A and leg B. In 3-phase we're gonna have leg A, leg B, leg C. You know what I'm saying? Just I call it DA, duty cycle for phase A. We call it DA VDC, right? This is. I want to calculate this DA now. I want to go calculate this DA. How much is this DA? So, if I want to calculate the DA, I need to find the relation between this T on and this TS, right? How much is this one? How much is this one? VTRI cap, right? This is a VTRI cap, correct? Yeah, cap means max. Yes, VTRI max. Yeah. And this one is V control. What is the V control? Can somebody tell me? V control. What is the V control? Is it this or not? Right? That's V and sine theta, right? If you want a sine output, you select your control sign. If you want a crappy waveform, you select the crappy waveform for control, right? But that's the V and sine theta. That's the V control, right? Now I need to go through this triangular. I'm going to plug it. Let's look at here. This time is a T off, right? This is a T off, right? The time the switch is off. This time, how much is this time? 2F over 2. Why? Because it's symmetrical, right? This is a T off over 2. Now, let me see. How much is this time? How much is this time? 2.
T on over 4?
T1?
T on over
TS over 4, right? This is a quarter cycle, quarter cycle, quarter cycle, quarter cycle, right? So this one is a TS over 4. I'm gonna plug these two triangles here again. I have one here, one here, one here, right? This one is here. This is a TS over 4, right? How much is this one? T off over 2, right? How much is this one? How much is this one? VTRI caps, right? How much is this one? V control. V control. And how much is this one? Yes. VTRI minus VCon, right? Let's give it a name. A, B, C, D, E. I don't know what term do you use in English, but I think this is what I use, the exact translation of Persian, what I learned 20 years ago, maybe 35 years ago, something like that. We say triangular ABC is similar to triangular ADE. I'm not sure if you guys use the same term or not. We say similar triangles? Yeah, so that's good. So this triangular is similar to this triangular Y. Can tell me why? I'm not going to go to the geometry and those things, but anybody knows why they are why they are similar?
The same
They're
angles.
B and D are both right angles.
Right angle, or you can say this angle is the same for them, or you can say this one is parallel with this one. These are all you have from geometry. But they are similar. You don't have to go through that. Don't worry. Now, if the triangular they're similar, what I can write, I can say this one over this one is equal to this one over this one is equal to this one over this one, right? You can, I think for GRE you have to go through this kind of things, you know. And now I'm going to write this. So basically, it's going to be AB. I write it here. AB over AD is going to be equal to BC over D, right? This is from the math. We know our geometry, math, but we know. Let's replace it. Forget the math. What is AB? VTRI minus Vcon, right? VTRI cap minus Vcon over. How much is AD? VTRI cap, right? Equal to. How much is BC? T off over 2. How much is the DE? TS over 2, right? Let's just find that. In this problem, we know how much is the TS, we know how much is the VTRI, we know how much is the V control. I want to calculate T off. If I calculate T off, how much is T on? Is it TS minus TF, right? TS minus T off. So basically T off is going to be, if you calculate this one is going to go here. It's going to be TS over 2, if I'm not making a mistake. This one is 1 minus Vcon over VTI. Right? Right? This is the T off. How much is the TS? Oh, sorry, T on. How much is the T on? Right? So one cycle. This much is off, the rest is on, right? So I have the T off, let's subtract this thing. Basically T on is going to be, I think it's going to be TS over 2, 1 plus Vcon over VTRI. Right? So I calculated T on. Now I'm going to go back here. Right? I have how much is my T on, so I can calculate my dA. How much is the dA? How much is dA? Is T on over TS. So basically TS is going to cancel TS. So how much is going to be? Right? So how much is going to be VAN? VAN is going to be right? Keep this one. This is not what we want. This is VAN. In a half bridge, see this is general. See what I did here is general. Just I use this leg, right? I say this one is on, this one is off. How much is this voltage? And I don't care about this part, right? If this one is on, how much is this voltage? VDC, right? If this one is on, how much is this one? 0. And the reason I'm saying forget this part, because what I calculate for VAN, it doesn't matter what is here. So basically, for the full bridge, I'm going to have 2 of these legs, right? I can apply the same thing to the second leg, right? For the three phase, which we are going to have it later, it's going to be 3 of these legs, right? So I can use the same equation. The only thing that is different for those one, V con is different, right? For the second leg was, for this one, the V con was this one. For the second leg, we have the same one, so basically it's going to be the same thing. But if it's different, the only thing that I need to change is a V con, right? Whatever is for that leg. Now, let's continue on the half bridge to see what we are going to have for a half bridge. How much is the VAO? How much is the VAO? VAO, is it correct to say VAN minus VON? Right? I can write it this way, right? How much is the VON? VON is VDC over 2, right? O N, right? Is a VDC over 2. So how much is the VAO? So it's going to be VAN, I had it somewhere here, right? VAN minus VON. Basically, we are going to get rid of the VDC here, right? So it's going to be VCon over VTRI, right? Cap times what? VDC over 2, right? Am I right or not? Let's see. Yes, that's correct. So, what is VCon? Is a VM sine theta, right? So, VCon over VTRI cap is going to be VM over VTRI cap, right? Sine theta, right? Is it correct or not? We said VCon is a VM sine theta, right? That's a sine waveform, right? What is this? Check your notes. That's MA, modulation index, right? Where when we say the sine PWM, we say the maximum of the sine waveform divided by the maximum of the triangular waveform, we call it MA, modulation index. So basically this is the MA sine theta. Now replace this one here. Replace this one here. I'm going to use this one here. How much is the VAO? I'm going to replace this one with this. It's going to be MA VDC over 2 sine theta. This is VAO over 1, sorry. Sine theta is the first harmonic, right? Theta is omega t. Right? This is the fundamental harmonics of the output. I don't have the rest of harmonics here. But what I did calculate, I know the V1 max is going to be this much, right? So V1 max, how much is it? Now if somebody tells you, hey, I want to have a sine PWM inverter with the MA 0.8 to use at my home for my computer, how much battery should I put there? At home, how much you need? 110 times the square root of 2, right? That's what you need. How much did he say I'm going to use MA? 0.8. You put it here and calculate VDC, so how much it is. We talked about this one. If MA is less than 1, we call it linear modulation. If you go more than 1, they call it non-linear modulation. We'll talk about that one in 3 phases, I'll go through the graph for that one. But look at here, this is the fundamental, this is very important. Fundamental of the output. This is very important. There are more harmonics, but this is the main one, the one I care about it, This is the one is very important for me for power transfer and everything else. Right? Any question on this one? How did we get here? Any question? Sometimes if you don't have question, there are too many. One is you completely understand it, the one is you didn't understand at all. Which way is correct here? I don't think that there is anything to not understand, but maybe the first time you guys are seeing it a little bit, we need a little bit more time to digest it. Just look at it, what I did. I started from here, I said I have a triangular waveform, I have a control waveform, the sine wave. Why? Because I'm going to get the sine wave for the fundamental is going to follow this sine waveform I'm putting here. That's the reason they call it sine PWM. What I'm getting in the output, look at here, is getting exactly similar to that sine waveform I'm putting there. The magnitude, the amplitude is different, but the phase is exactly the same. Yeah.
But do you choose MA? Is that something that's...
MA, you're going to work a lot with, that's the control parameter later, But if it's an open loop, inverter, you have to choose MA. You choose MA whatever you want. But when it's a control loop, the control loop is going to, we limit MA to 1. We don't want to go more than 1 because we're going to get to the nonlinear modulation. That's when we get to the control part. We get to explain that. But MA could be any value between 0 to 1. You should select the right value to give you the right voltage. For example, in this case, it says 110 volt. You should select the right MA. First, you should select your VDC correct. If you select very low VDC, no way MA can help you. You know what I'm saying? Let's put 10 volt here, right? If you put 10 volt here, how much is the VDC over 2? 5. MA could be maximum 1, right? No way you are going to get to the 110 times the square root of 2, right? But if the VDC is 300 volt, you can calculate the minimum value for MA, right? The minimum value for MA is to give you 110. So basically, say, okay, the minimum value for MA is 0.7, for example, based on what is my VDC. And it can go up to 1. But up to 1 is a control parameter. There are some of the things happening in the circuit. You have to change MA. We'll talk about that one later. This is your project is going to be exactly calculating this MA, the control loop for the three-phase inverter. This one was a half bridge. Let's look at the full bridge quickly. It's going to be very fast. This is a half. This is a full bridge. Let's call this one A, this one B, S1, S2, S3, S4. You are on the bipolar switching. Still, we are talking about the bipolar switching. Bipolar switching, we know S1 and S4, they are the same. We use the same control waveform. The same thing here. Exactly what we have here. So how we are going to switch? If, and let's call here AM. Let's call this point N, right? So if we use the same thing I put over there, we say if control is more than triangular, right? So S1 and who? 4, they are on. How much if S1 is on? How much is this one? If this one is on, this one is connected here, this one is connected here, right? It's the VDC. How much is the VDN if S4 is on? 0. Now another case is going to be if V control is less than VTRI. Basically S2 and S3 they are going to be on. So let's see what's going to happen. If S2 is on, how much is the VAN? 0. How much is the VBN? VDC. Basically, look at here, VAN, these two cases is exactly what we had over there, right? What we went through. Nothing changed about VAN. Now, how about EBN? See, I know VAN is this much. Alright? This is what we have. Can somebody tell me how much is VBN?
Just that, without the divided by 2.
Look at here. Go back here. How did I calculate VAN? T on over TS, right? T on for switch 1. For switch 1, right? Be careful which switch we are here. Well, TS is TS, right? And VDC is VDC, right? How about if I'm going to calculate the VBN? I should see how much the switch B is on, right? Divided by TS. How much switch B is on? How much switch B is on?
TS minus T out.
TS minus?
T out.
T on? Why? T off. You're right, but why?
Just one, both switch cannot be on at the same time.
No, because if you look at here, we said if this one is on, this one is off, right? If this one is off, this one is on, right? So off time for this one is on time for this one, right? Basically, if I'm going to calculate the VBN, it's going to be like this. VBN is going to be T on for switch number what? Number 3, right? For S3. T on, but be careful. This is for S3. When S3 is on, right? If you go here, this one was for which one? S1 on, right? When you say T on, this is when the S1 is on, right? So we said T on when S3 is on over TS. Right? T on when S3 is on is equal to what? T off when S1 is off, right? T off of S1. How much was the T off? Yeah, somewhere here. Right? So basically T on for leg B is going to be VDC, not VDC. TS over 2 1 minus V con over VTR, right? So now I know how much switch number 3 is on. I know how to calculate VBN. Just I replace this one here, right? How much is the VBN? I replace the T on with this one. So TS is going to cancel TS, is going to be VDC, is going to be, there's a VDC here. Right, there's a VDC here. It's going to be VDC over 2, 1 minus V con over VTR, right? Right? Clear? But what I need to know is my load. This is my V load, right? Right? How much is the VO? VO is a VAB, right? Or is a VAN minus VBN, right? VBN is this much, VAN is this much, just subtract it, right? So it's going to be, see, VDC over 2 minus VDC over 2. They cancel each other, right? But the next part, VDC over 2 times this minus VDC over 2 times minus this one. Minus and minus is going to be plus, right? So basically it's going to be 2 times VDC over 2 times V con over VTRI. And we said, what is this term? It's going to be MA sine theta, right? This term was the MA sine theta. This 2 is going to cancel this one. It's going to be MA VDC sine theta. Basically, VO first harmonic is going to be MA VDC. What's the difference between this one and that one? Half bridge and full bridge? Here we have the voltage is double, right? Over there was the VDC over 2, here is how much? VDC. In this case, if you need a 200 volt battery, how much battery do you need over there? 100 volt battery, right? That's the difference between these two. Again, they call it bipolar because if you look at here, I'm going to see it, put it here. If you look at here, either VAB is VDC or VAB is minus VDC, right? Bipolar, either VDC or minus VDC. VDC or minus. That's the reason they call it bipolar, switching.
How come for this we can use the VAN for the half bridge in our full bridge calculation?
No, see, the reason was I didn't change my control, right? The waveform I had here, the triangular and the control, I said this is the one I'm using for leg A, right?
Yeah, but if in that circuit, then wouldn't VAN be like VDC instead of VDC over 2? Like wouldn't that equation be VDC instead of VDC over 2?
No, it's going to be, I did it there. So what I did here, I said, okay, VBN, like exactly what we did here. But how much was VAN? The time the switch S1 is on, divided by TS time VDC, right? Here is going to be the time switch S3 is on, divided by TS. And this time I cheated here. I said, okay, the T off here is T on toward out, because I put it there. But now we have another type of switching. I call it bipolar switching. Not bipolar, the unipolar switching. The waveforms are a little bit different. You have to go through that one. I'm not going to calculate it, but you have to go through that one. If you go to three-phase inverter, we're going to talk about it in detail later. But if you look at three-phase inverter, there are 3 legs. Leg 1, leg 2, we call this one leg. So you can think of one of this one, we call it leg. Leg 1, leg 2, leg 3. You're going to have one output here, one output here, one output here, basically the 3-phase output, right? When you go to three-phase inverter, again, you have a carrier waveform. Now, for phase A, if you go back to the energy conversion or the first class of the power electronics 1, we said in a 3-phase system, a balanced 3-phase system, phase A is a 0 degree, phase B is a minus 100 degree, 120 degree, phase C is a plus 120 degree. And all of them, they have the same magnitude, right? So basically, I'm going to select my control waveform. I want to have a 3-phase output voltage balanced, right? So I can select this one for my phase A, right? This is the VA control, V con A, right? For B, what I'm going to do, I'm going to use the same waveform, shifted 120 degrees. It's going to be something like this. This is B, V con B. For C, I'm going to shift this 120 degrees. It's going to be like this. This is V con C. So basically, now you can say VAN, the same thing I calculated here. How much is the VBN? Can somebody tell me? VBN is exactly like VAN. The only difference, if you look at it here, what is this V con here? Is a VM sine theta, right? This is what we have for VAN, right? How about VBN? VM sine theta minus 120, right? That's exactly the same waveform, just shifted 120 degree, right? How about for phase C? The same thing plus 120 degree, right? We'll talk about this one later. I'm saying this is the approach we use for single phase, half bridge, H bridge, and 3-phase inverter. Now we went through this thing, we know how to handle a half bridge and full bridge. I want to go through one example, That's the bad part now. Let's look at this table. Let's look at this table. Here we're going to use the one you have it in the book, Daniel Hart. It only shows this part, this part, only this part, not more. But it has more points. It's calculated for MA 0.1, 0.3, 0.1, 0.2. Look at here. There is an MA value, the top one. What was MA? Here we had somewhere. I wrote it somewhere here. This one. How much was this one? This is the MA. VM over VTRI, right? This table is calculating all the harmonics for the bipolar switching. And it makes your life easy. Think about it, if you're going to calculate all these harmonics yourself, that's a Fourier series, how much of work it is. So you will use this table for your homework. This is a very, very helpful table. Let's go through it. What does it say? This one. For example, we have a inverter is going to work with MA. Let's start with the last one, MA1, right? The maximum of the sine waveform is the same as maximum of the triangular waveform, right? That's the last column here, right? If you look at here, here it said the MA 0.2, 0.4, 0.6, 0.8, 1, right? It'll stop here. It's not going to go more than 1. Because if you go more than 1, it's going to be non-linear modulation, right? So the right behind this one, it said the fundamental harmonics. This is normalized. It's not putting the VDC or VDC over 2. See, this one has a VDC over 2. If you divide this one, let's say V1 max over VDC over 2, how much is it? Is MA, right? We said it's normalized by half a VDC, right? Or if you normalize here, VO1 over VDC, how much is it? Is MA, right? And you can see here it said, look at here, right underneath, it node VAOH. H is the number of harmonics. This is for the half bridge, but you can use it for the full bridge also. The only difference is VDC, right? Is the VDC over 2. It is giving you this equation here, right? Now let's look at this table. So basically, if MA is 1.1 is 1.0, how much is my normalized V1? How much is it? Right? How much is it? V1? MA, right? So in the last column, how much is the MA? MA is 1. So basically, how much is my first harmonic? 1, right? Let's go one back. When MA is 0.8, how much is my V1? 0.8, right? When MA is 0.2, how much is my V1? 0.2. Guys, I'm going to go over this one until 6:30, something like that. I need to finish the example, you know. I want to finish single phase today. Now, look at the next row. Not row, next section. There's the MF. What's the MF? What was the MF? Right? For example, you want 60 hertz output, this one. Whatever is the frequency of this one, right? The frequency of this one is 60 hertz or 50 hertz. Usually that's a very common number, 50 or 60 hertz, right? So F is 50 or 60 hertz, FTRI is 5 kilohertz, 50 kilohertz, 100 kilohertz. Think about it, how big is the MF? If it's 5 kilohertz and F is 50, MF is 100, right? 100 times 50 is going to be 5 kilohertz, right? But MF, we call it frequency modulation index, right? That was a frequency modulation index. MA was modulation index, right? We talked about this too. Now, what it says here, it said, hey, the next harmonic you are going to see is going to be MF. Think about it. MF. If MF is 100, I'm going to have the first one. The next one is going to be 100th harmonics, right? Can you see the advantage here, what's happening? Remember through the example we went? You know, when the voltage harmonics number is going up, the current is going down, right? Why? Because we had N omega L, right? Let's go to the example for this one. My point is, if, for example, it's good to have a, let's say we are going to have a third harmonics 5 volt is better, or 100th harmonics 5 volt is better. They give me a choice. They say, hey, you could have a converter, it could have a generator third harmonic. We have first harmonics, right? That one is there. We have to have that. This one is going to give me a third harmonics 5 volt. This one is going to give me 100th harmonic. There is nothing else. There is a 1 and 3 and 1 and 100, right? Which one do you select? 100. 1. You say we select the one that has the 1 and 100. Why?
100 actually lasts.
What?
100 actually lasts
in the current. If you look at IN, it's a VN, right? If both of them, let's say 3 and 100, both of them they have 5 volt amplitude, right? So this number is the same. But for 3, n is how much? 3. For 100, n is how much? 100. Think about how smaller the I100 is going to be compared to I3, right? So what's the meaning of that? Better TH before the current, right? Better TH. So you can see here, with using this one, this technique, opposite of what we had before, we had just a square wave or a little bit more like a half bridge or full bridge, and or harmonic elimination, right? Harmonic elimination, we can eliminate a few of them. This one, if you select very high MF, it's going to go all the way here, right? We have the first harmonics here. The next one is going to happen, is going to be all the way here, right? That's a good thing. Now we are pushing harmonics rate. We are not getting rid of all of them. Yes, they are going to be big. You can see the table. But the good thing is the number of harmonics is very high. In general, for bipolar switching, you are going to see this kind of harmonics in the output. Let me write it right here. This is a note from one of my students. He wrote it last year. I asked him to give it. Believe me, you don't know how many mistakes it is. Even today, I was reading it myself, to remind. I couldn't understand it. Finally, I went back to my old note. The one was crappy. That's why I figured out what did I teach last year. I was going to put a copy of this one on the website. When I saw all these mistakes, I said, no. I'm not going to do that. For this one, bipolar switching. The harmonics in the output, Fn, the frequency of the, let's say n is the number of harmonics at the output, is going to be J MF plus minus K times F or F1. F1 means 60 Hertz or 50 Hertz, whatever you select, the one you select. And the other thing is if J is, these are integer number. Both of them are integer number. So if J is odd, K, then K should be even. And if J is even, then K is odd. This is a math, you should write the Fourier series, all those kind of things. You're going to end up here. But let's go through this table now. Because I want to say, how did this number they came in? The number we have in this table. Let's go over it to see what it is. Look at the table, the first row. Let me put this table here because this table has a good meaning, maybe it's better to go over it. There's an MA here. H is the number of harmonics. H put it here is the number of harmonics. And here you put a 0.2, 0.4, 0.6, and 0.8, and 1. I'm not going to write all the numbers here, it's going to take time. So you said the first one, if harmonics is the number 1, V1, and this is normalized, right? We said is over VDC over 2 or over VDC. How much is the magnitude of harmonic number 1? Whatever is the MA, the same thing here, right? So it's going to be 0.2, 0.4, 0.6, 0.8, and 1, right? Now, what is the next harmonic one? What is the next harmonic I'm going to see in my output? MF. Right? And based on this equation, so J is 1, right? So it's going to start from, because this is a odd number, this one should be even, right? It's going to be MF plus minus 2, MF plus minus 4, MS plus minus 6, Basically, it's going to be like this. MF plus minus 2, right? Because J is 1. Think about it. This is a J, right? So it's going to be MF plus minus 4. I'm not going to put more here because, look at it here. Look at the table. It is calculated. Even for most of them, MS plus minus 4 is going to be 0. See, you can see it's white here. If you look at the table, you can see it's white. There is no value for those ones. So basically, this one is going to be gone. There is nothing here, right? Only there is these two. The next one, what's the next harmonic in the output? J should go up, right? We have J1 here. The next one is going to be 2MF, right? But if J is even, now K is up. So the 2MF plus minus 1, right? 2MF plus minus 1. 2MF plus minus 3. 2MF plus minus 5. You can see it here. 5 is almost all of them, they are 0, right? What's the next number? J is going to be 3, right? If it's 3, it's going to be 3MF, 3MF plus minus 1, 3MF plus minus 2, all the way. This table gives you all those numbers. See, you can see how much value this table has, you know. You should work on this one. Most probably you're going to, in homework, you're going to definitely use this homework. Maybe in the exam also I give you the same. Now we learn this, how this table works. Let's go through some examples. These are from Daniel Hart. Daniel Hart book is only using this one. Let me see which one it's using. If you go look at the Daniel Hart books, it is the page it is page 363. See here. It just shows MF1, sorry, first harmonic, MF, and MF plus minus 2. It shows only this one. It gives you only this first 3. It doesn't show the rest. If the rest is not that much, critical, but it's kind of very, very short version of this table. This table is an extensive table. It has everything until I don't know how much, what kind of harmonics, So, but now, I'm going to use either I can use this table or that table, doesn't matter. Either way, that one is a little bit more accurate, So, let's go through this example. Example in page 363. It says a full bridge inverter is used. Full bridge inverter is that one, right? Is used to produce a 60 Hertz voltage across a series load, RL series load. We have a RL load here, right? And we have a 60 Hertz voltage here. So F is 60 Hertz. And we have an RL load. It says the DC bus is 100 volt. The DC bus is 100 volt. The amplitude modulation ratio MA is 0.8. It's giving us the MA. So basically, when you give us the MA 0.8, I'm going to come use this part of this table, right? So you look at here, this is the MA, right? I'm going to come use this column of this table, right? So the amplitude modulation ratio MA is 0.8, and the frequency modulation ratio MF is 21. It's telling me MF is 21. Okay. Now, the load has a resistance of 10 ohm, and it says R is 10, and L is 20 millihertz. Determine A, the amplitude of the 60 Hertz component of the output voltage. 60 Hertz is which one? Is a fundamental, right? 60 hertz is the number one harmonics, right? It says how much is the V1 maximum? Somebody tell me, how much is the V1 max? Either we can use this table, or we can use this one, right? How much is the V1? MA times VDC. Or, as he mentioned, you can come to this table. See, this is the V1, right? How much is it? 0.8 or MA, right? Times VDC. So it's going to be 0.8 times how much? 100 is the 80 volt. This is the maximum value, right? Keep in mind, this is the maximum value of the output voltage, 60 hertz component. So we calculated that. The power absorbed by the load resistor. He said how much power this resistor we have here is going to absorb power. How should I calculate that? V. No, we're not going to go that way. We can do that one, but we're not going to go that way, you know. We say P is a sigma PM, right? Every harmonics, right? And from 1 to 11. So basically it's going to be R I1 RMS to the power of 2 plus R, whatever is the next harmonics. IN, let's put it this way. Right? The rest of the harmonics. So it's basically what should we do to calculate the power absorbed by the resistor? I should calculate I1. I don't know what's the next harmonic? Think about it. MF is 21. What's the next harmonic? 21. I should calculate V21, right? And what is the next two? 19 and 23, right? I need to calculate. We're not going to go more than here. You can, if you want to be more accurate, you can go all the way if you want. We're going to use only this number up to here. This is the approximation, you know. Just let me complete this table for those two numbers. If you complete this one for this, it's going to be MF is going to be here is going to be for MF is going to be 8.8 this much, and for plus minus 2 is going to be 0.22. And for this one is 0. Even you don't have to go there because this is 0 already, right? So there is no point to go there. Now, yeah.
Doesn't 2 MF plus or minus 1 have larger values than MF plus or minus 2?
No. You can see here this one has a larger value. It is almost the same as the fundamental frequency. I had to put a slide to show you, but as I said, because we don't have this HDMI cable, I cannot. You know, if you look at it here, there is a harmonic spectrum here. I was going to show you this one. This is the harmonic spectrum, you can see here. This is the fundamental, and this one is almost the same as fundamental. Yes, it's very big. The voltage THD sucks. Because this one is like the fundamental, right? But the current THD is going to be really big. Why? Way back over there, right? And the one is important for the utility is current THD is very important, right? So now let's go through this example, finish it. So what I should do, how much is the IN in general? How much is IN? Right. How much is the omega? 2 pi f is going to be 377, right? R is 10. Okay? Now, how much is the V1? 80 volts, right? I'll write it here. V1 is AV, so I1 is going to be 6.39. So how much is the P1? How much is the P1? R times the RMS value of this current to the power of 2, right? Is going to be 10 times 6.39. This is the maximum value, right? I should divide it by square root of 2 divided by 2. Divided to the power of 2, right? So if you calculate this one, is gonna be 204. Based on the experience we had from the last class, right now I can even forget the rest. Remember, I calculated everything. More than 95% was transferred by first harmonics, right? And I said usually we don't care about the rest. But because this is the first time we are going through this harmonics, let's calculate a few of them, right? The next voltage we have in the system is going to be 21, right? MF, right? MF is 21. This is the next harmonics we have in the system. How much is this one? 0.818 times VDC, right? So basically it's going to be 0.818 times 100, 81.8. And here, this is when I said the TH4 voltage stops. Look at here. This is 81.8. This one is 80. This is even more than this, right? But let's look at the current. How much is the I-21? I-21 just you should put here and 21, right? If you calculate I-21 is going to be 0.52. 0.52. Right here, 0.52, 6.39. See how much there is difference? And you can calculate the power for this one, P21. If you calculate the P21, it's going to be 1.31. 1.31. This is the big guy. Among all those bad guys, this is the big one. How much is it? 1.3 watt. How much is this one? 200 watts. It's 0.5%. That's the reason I'm saying hey, we don't care about the rest of the harmonics. The first one is going to give us there. But let's go through the, as I said, this is the first time. Let's go, what are the next harmonics in the output? 19 and 20, 23. How much will be 19? How much will be 19? See, I should go through here, right? MS is 21 plus minus 2. Minus 2 is 19 plus 2 is 23. How much is it? 0.22 times VDC, right? So 0.22 times VDC. Basically, this is a V23 also, right? Because they are the same. V23 and V19, they are the same. So it's going to be 22 volt. How much is the I-19 and I-23? 22, right? Oh, no, we cannot write it this way. We cannot. It's going to be 419, it's going to be 19 times omega L, right? 423 is going to be the same thing. Right? If we calculate these two values, I-19 is going to be 0.15. These are the maximum value I'm putting here. And I-23 is going to be a little bit less, 0.13. This one is going to give us a P19 of how much? P19 of 0.1 watt. This one is going to give us again the same thing almost. 0.1 watt. A little bit less than even 0.1, but just a 2.1. See? How much is the power absorbed by the resistor? PR is going to be this one plus that one is going to be 204 plus some, I'm going to say 204, right? And 204 watt. Basically, it's going to be 1.5. It's going to be 205.1. So you can just calculate the first harmonic and calculate the power, right?
How to make the voltage, how to make the voltage and current flow almost the same?
Current, the voltage, you have to use the C filter. See why the current is looking better here? Because we have an L filter, right? RL load, it has an L, there is no capacitor here. if you're going to clean up the voltage, you need to have a C filter. We'll get there, and we'll go there, The last part is asking how much is the THD for the current. ITHD. See. How much is the ITHD? The non-fundamental, 0.52 to the power of 2 plus 0.15 to the power of 2 plus 0.13 to the power of 2. We're not calculating the rest, right? Divided by how much? 6.39 times 100 is going to be 8.7%. If you want to make it better, let's assume there is no resistor to make our life easier, right? If I make the MF 2 times, instead of going at 21, I go 42. What is going to happen? 42. The voltage is not going to change, right? But the I-21 is going to become half, right? It become 0.25, right? I get rid of the R to be able to linearize it, right? It's going to be 0.26. And this guy, they're going to be 0.05 and 0.05, right? So to calculate the THC, maybe it's 4%, I don't know how much. So I'm saying you increase the MF, your current THC is going to get much better, right? So this is one example. They gave us, we have this inverter, blah, 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 calculate this thing. But usually it's the other way. I want you to design an inverter for me. To tell me what MF should I want. Those kind of. Next example. Let's look at the next example. I like the next example whenever we're going to do design question. And usually design are more difficult than the one, because design, you have to assume some of the things, and those kind of things. Well, look at here. If you go with the THD, this one is going to be 0.25, right? To the power of 2 is going to be 0.20, because I'm going to use this assumption now. 0.5 to the power of 2 is 0.25. How much is this one? 0.01 or 2, something, right? 0.01 or 02, right? So these two, they are much, much smaller than this, right? Even I can get rid of this 2. Because the THD is basically based on this one, right? I'm going to use this concept for the next problem, I'm going to go with this one, only this one for the THD. Now, the next problem is saying this. I'm going through these examples because I want you to learn the basic of the inverters, what does it mean, this kind of thing. And unfortunately, again, I cannot finish this. There is one more thing that I want to talk about. But I'll leave that one for now. Let me finish this example. The next example is say design a bipolar PWM inverter. See, this is on page 364. Right after that example. It said design a bipolar PWM inverter that will produce a 75 volt RMS. So my output V1 RMS is 75 volts. See, when you say the output is 75 volt, is not the third harmonics or I don't know 100 harmonics. The one we do care. Which one we care about? That's the first harmonic, right? When you have a 60 hertz, that one is for you important. You don't care how much, you care how much is the 180 hertz, 240 hertz. You want them as small as possible, the rest, right? The one you wanted to have right 110 volt is the 60 hertz, right? You said we want to design a PWM inverter that has 75 volt out, RMS. And 75 volt RMS 60 hertz is giving us the S. It said it's a 60 hertz inverter. And from output from a 150 volt DC source. VDC is 150 volt. You said we have a battery is 150 volt, right? It said the load is a series RL combination with R is 12 ohm and L is 60 milliamp. In this case, R is 12 ohm and L is 60 milliamp. select the switching frequency. Now it's telling us what frequency should I select for this one. Select the switching frequency such that, see, this is important, such that the THD of the current is less than 10%. We want to have the THD, ITHD less than 10%. What frequency should I go? What is the FSW? Or FS, I call it FS, previously I called it FS. What switching frequency should I go? You can see here. What did I say here? I said if I double the frequency, switching frequency, right? MF was 21. If I make the MF 42, my THD instead of being 8 point something, most probably it's going to be half almost, right? It's going to be 4%. So you can see the relation between the switching frequency and the THD. If I go higher on the switching frequency, or I will have a higher MF, right? I'm going to have a lower THD, right? That's the reason he's asking you, what switching frequency should I select to have a THD less than 10%? Usually they say less than 5%, not 10%. But this is an example, that's normal, right? So now let's go back here. I'm going to go do this one. I said, okay, he gave me what's the first harmonic, right? 75 volt. I know the switching, the frequency is 60 hertz, right? What I can do, I can go calculate my I1, right? I know this one. I know R. I know N is 1 for the first one, omega everything, right? I calculate my I1. If I have my I1, right, and I get up the rest of this one, right? So this is bad. What I'm doing here, so be careful. If I go just with this one, THD is going to be a little bit smaller. Maybe if instead of 8.7 would be 8.2. Keep this in mind. My number I'm calculating is a little bit better than what it should be, but I will compensate for this one later, So I said, okay, I know how much is my I1, right? I get rid of all this one, and I know how much THD I want, right? I can calculate therefore the MF. How much is the IMF, right? If I know how much is the IMF, here, go back here. If I know how much is the IMF, I can go back and I know this one, so I can go calculate the N here. How much is the N? If I know N, I can calculate back the MF. Let's go over to see what's going to happen. So we have the V1 RMS here. First, I want to calculate MA. How much is the MA? Somebody tell me, how much is the MA? We said the MA, if you remember, we said V1 is the MA VDC, right? That's what we had for this one, right? How much is the MA? Why I'm calculating MA first? Why? Why? I want to know where I should go in this table, right? I should know where I should go to this table. So MA is V1 over VDC. How much is the V1? If this one is more than 1, I cannot use that table. If it's more than 1, I cannot use that table. Be careful. But it's not. It's 0.7. So we don't have that one here, right? So what you do, you have this table and this one, just interpolate it, right? Let me put these numbers here. In Daniel Hardwood you have a 0.7, but here we don't have it. If you go here for 0.6, it's going to be 1006, and for this one it's going to be 131. So how much is 4.7? Add these two numbers, divided by 2, put it there. Add these two numbers, divided by 2, put it this way, right? This is approximation, this is engineering design, you know what I'm saying? It's pretty accurate, don't think this is not accurate, but this is the way we calculate. If I cheat and use this book, which has numbers, they're going to be a little bit different from this one because this is more accurate. If you put the 4.7 here, you're going to see this number. 4.7, if you put, it's going to be 0.7, and this is 0.92. Look at here, 1.8 is 0.9, right? I'm saying this is not bad. The accuracy is not bad when you look at it. And 0.13 and 0.17. This is 35, right? it's going to be 1 point, if you do the interpolation, it's going to be 0.175, right? Now let's go back there. We know the MA is 7.07, we go with 7. We assume MA is 7, we go with that. So we are going to use this part of this table, right? How much is the V1? 75, right? How much is the I1? Is a V1 over R squared plus omega L squared, right? Omega is 377, L is, I don't know, 60 millihenry, R is 12, V1 is 75 times square root 2, right? So I1 is going to be 6.39. Now, what's the next harmonic? Is MF. I don't know what's MF. What is MF, right? I assume, this is important, assume THD, ITHD is almost equal to IMF, right, over I1 times 100%. Basically, in this summation, if I get rid of all this one, this is IMF to the power of 2, right? The square root of that one is going to be IMF, right?
In that case, we get rid of all those extra terms.
Yes.
Can we just use it like the requirement is 10%? Let's set it 8%.
No, I'm going to compensate it other way. Hold on. You know, you can do it. You can do the compensation. And what you do, whatever you select later, you should go back, like the previous example. Solve it again to make sure your THD is less than what they asked. Double check that, you know. But the way we are going to do it is going to be definitely, you know, less than that. Now, I know my I1, and we said this should be less than how much? 10%. So basically, IMF over I1 should be less than 0.1, right? So how much is I1? 6.39. How much is IMF? Should be less than 0.64, right? 0.64. So I figured out how much is going to be IMF, right? Now, I'm going to go back to VMF. How much is the VMF? Can somebody tell me? How much is the VMF? How much is the VMF? See, I'm using MF because I don't know what's the MF, right? He asked me what's the switching frequency, just said okay, MF, right? I'm going to go with MF. VMF, how much is it?
IMF over
0.92 times VDC, right? I don't know how much is that. It's like 0.92 times 100, right? Whatever. Now, how much is the IMF? NF basically is the end, right? Right? And we know our IMF should be less than how much? 0.64. Let me see, how much is this one? Looks like the VMF here is 138. So this one is 138. This one is 12. This one is 60 millihenry. 377, right? The only unknown is what? MF. If we calculate this one, we said MF should be less than 14.7. So, what number do you select? A little bit higher. A little bit higher. That's lower. First of all, integer number. We cannot have an MF 14.7, right? So, what's the next integer number? 15. Remember, the higher switching frequency, the better for THD, right? 15. But very close to 14.7, right? A little bit more than that. I had all this assumption here. I didn't count it, right? Let's go with MF17 to make sure we are clear, right? So, how much is the switching frequency now? FSW. 70 times 60. Go double check the THC. For sure it's gonna be less than 10%. For sure it's gonna be less than 10%. Okay, we're gonna stop here.
Explain.
I can't, I'm gonna finish what I want. So, oh, here one, do you remember here what I said, when I went through this one? For MF21 divided by 8%, right? I explained this, and let's forget this one, right? Because if I would have gone with the MF42 two times, this one would be half, 0.26. This THC would be smaller, right? So basically, if I want to have a better THC, I should go with a higher MF, right? So this one is said MF should be less than 40.6. No, I'm not here. Hey, here, guys. This is more than. This is greater than 40.7. You know. So the next one is a 15. 15 is pretty close. You can select that one, double check. Most probably you're going to be right at 10%. But usually when you design, you want to have a little bit more. You want to say I'm going with 17 or 9. 9 is better than what I want, right?
Is there gonna be a discussion today? Is there a discussion today?
Not today, but April, I'm not sure, the 21 or 22nd, I'm not going to be here. I have asked for the next class to see if we can reserve the class. From Wednesday, I'm going to go like 20 minutes more every classes for like a 4 class to cover what the session I'm not going to be here. If you guys are okay, I'll go 20 more minutes. We should finish 6:18. 20 minutes, then 6:40, right? Yeah, 22 minutes. Cheating. Then 6:40. But let me make sure the class is available on this for the conversation.